Problem is, when you actually try to set them, they don't work. So some reverse engineering needed to happen, and I figured out how to find the kernel trap frame. Now I'm going to show that to you on a diagram. If you can find the kernel trap frame, you can set anything you want, DR registers, EIP, for the user mode thread. As soon as it transitions back into ring 3, all your context immediately becomes live. It lies at the bottom of the kernel mode stack. To find it though, don't trust the pointer that's in the EThread block. It lies. Instead, you can use the initial stack pointer and do a calculation. And I think I actually show that here. FS0 to the KPCR, go down to the current thread pointer, find the K thread, follow the initial stack pointer, and then there's a calculation you can do right at the bottom, and you'll see that you can set the DR registers and other things there. This needs to be done using a kernel mode APC call. Now we're going to use it to control both EIP and the DR registers. Now we need to schedule a kernel mode APC to actually do the work for us. So I'm going to show you that. I think I'm going to show you that. Nope, I don't have the source code up. So every thread, you can schedule APCs. There's two kinds, kernel mode and user mode. The problem with user mode ones is if the thread's not in an alertable state, it won't actually execute it, but kernel mode APCs execute immediately. So we schedule the kernel mode APC with the information necessary to set the DR breakpoint. It goes live in the other thread. As soon as it's done, it sets a signal. We're waiting on it with whatever, blah, 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 over here. And when we kick out of it, now we're going forward again. So here we go. DR0, hardware breakpoint, render world, injected code page, back. And the Warden code does not see any modification. In order for this to work, we have to hook two interrupts 1 and 3. Interrupt 1 is a really neat one. It goes for single steps, branch trace instructions, ICE breakpoints, and hardware breakpoints. We're only going to use it for hardware breakpoints. And then we're going to use interrupt 3 as sort of a quote-unquote secret message channel, which I'll show you in just a moment, to communicate back and forth from the injected code. So we have to hook the debug interrupts. The problem with this is now you can't use WinBag or soft ice. You're out of the water because you can't have two debuggers on the system. So one of the things I had to do was develop a serial port console so that I could even debug my own driver because I got really, really tired of trying to debug crash dumps. Each CPU has its own interrupt descriptor table, so we actually have to make a deferred procedure call to each of the processors in order to have all of the IDTs get hooked. So if you see this here, imagine each processor has its own IDT. Here's some source code. We initialize a DPC, and then we initialize an event that we're going to wait on. We can tell how many processors are on the system with KE query active processors. And then we can set the target processor for the DPC. This is how you force code to run on a particular CPU in the system. KE set target processor DPC, insert it in the queue. And we don't have to wait, but that's the way I designed it. So we're going to wait for the DPC to complete and then move forward. And we do that for all the processors on the system. Here's the DPC routine itself. This one's pretty straightforward. We unprotect memory using the CR0 trick, register CR0. We then hook the interrupt table and then reprotect the memory and set the event. Pretty straightforward. Okay, now what happens when an interrupt fires? When the interrupt goes off, at the top of the stack is what's called a trap frame, and this is the information that's in it. If you modify the EIP and IRET, you will hyperspace the thread to somewhere else. So this stuff is very important. Now, we can't do a whole lot of processing when we get an interrupt. We have to schedule a DPC because what we don't want to do is hang around blocking up the computer. So whenever we want to do any sort of processing, we'll schedule a DPC, and then the DPC will take care of the work after this. Any modifications you make to the trap frame or the CPU context will be live when you return with an IRET. So this is how shadow branching works. There will be an interrupt event on DR0 because we have a hardware breakpoint. The interrupt 1 will get called. Inside of interrupt 1, our ISR will uncloak the memory, will change the EIP in the context, and IRET, immediately hyperspacing the thread to a new location. And then when the new location is done executing, we'll have a secret code which causes an interrupt 3 event at the bottom. And what that will do is restore the same context back and IRET, immediately hyperspacing it back again. So it's based on 2 interrupts. We don't have to hook the page fault handler. Okay, so when interrupt 3, here's an example. Interrupt 3 fires, we get the trap frame, we save the EIP, we save all the information in the trap frame, and we also store all the information in the CPU off, because we have to restore all of it when we restore these contexts to hyperspace back. So we have to save that in a global structure. When the rootkit is done running, we get another interrupt 3 event, and we basically overwrite the trap frame with the previously saved data, as well as restore all the CPU context, and we're back. Here's an example of my structure that I use to store everything. You can see which items here are read from the processor directly and which ones have to be read from the trap frame. Now, you can actually send commands between the injected code and the supervisor via this trick. Basically, you hard code an interrupt 3, and you put some kind of secret value in the EAX register or something, and that's the code intending to tell the supervisor what to do next. That is like cloak and branch back, etc. The trick I was using for quite a while is to actually hard code some instructions directly after the interrupt 3, and those were read as a D word. So they actually aren't push pop, but when the interrupt fires, I actually read in direction of EIP and actually read this as a D word, and that's my secret code. I know it's obtuse, but it does work. And there's the code that does it. You can see I'm switching on it down there. Secret code equals, and then it has this secret code mentioned right there. Okay, so to return from the interrupt, we can tell which EIP throws the interrupt, so we can have behavior based upon that. When we return, we also need to make sure we set the RF bit. That's very important, or otherwise we'll end up in a recursive loop. I don't want that. So there's the whole hook. So when the interrupt fires, we disable interrupts. We call a routine called getContext that loads all the context up. We call to a debug handler that I've defined. You notice I push ESP on the stack, add 24. That's so that I have the trap frame pointing, I have a pointer to the trap frame as the main argument to the debug handler. Then when we're done, we set the RF flag. I've noticed some discrepancies in the documentation here. Just set it yourself, even if the documentation says you don't have to. Here's the routine that restores context. Gobbledygook. So total round trip. Interrupt fires. EIP points to the code we are branching. We uncloak the memory page. We change the EIP, causing the hyperspace. The new code runs. When the new code run is done, it fires again, an interrupt, and we return back with the original context. And there's the actual implementation of the shadow branching. You can see I'm copying the context in and out and uncloaking the page. Here's the code required to set the RF bit so that we don't loop infinitely. Okay. Now, how do we cloak the memory? It's very simple. We can go through the page tables, and we can modify the physical address for a given page table entry and cause it to point somewhere else. The same virtual memory now points to entirely different actual memory. That's one way to do it. It's also very unstable. I actually have a second way to do it, where we just copy the memory in and out of a holding pen, and that seems to work very well too. So page table manipulation. The way that I had originally done it is I allocated non-page pool memory, so I didn't have to worry about being paged out, and I used that physical address as the remapping point when I have the cloak in operation. There's an entire path of places we could, in theory, exploit the system. We could exploit the register that points to the page tables. We could exploit the page directories or the page tables themselves. We exploit the page table itself to point elsewhere in RAM. Here's an actual diagram of how it works for non-PIE systems. CR3 has the physical address of the page table. You can see the virtual address here. The top 10 bits index into the page directory. The next 10 bits index into the given page table. And finally, the byte index is in 4096 into the actual page of memory at the bottom. The way that Windows does it is they actually stick the base of the PDE at C0300000, so you don't actually have to, you just basically get the base address of that and you take your 10-bit index and multiply it by 4. There's a little pound define macro I made to do that. But you don't actually have to look at that. Well, you do if you want to check to make sure the page table is not paged out. But the actual page tables are based at C0000, so you can just go straight there and use the entire 20 bits and multiply it by 4 and find the page table entry you're looking for. Now, PAE systems are slightly different. I figured I'd cover that because my laptop happens to be PAE. I actually had to implement this. CR4 will have the following settings if PAE is enabled. It just has a slightly different system. It has up to 4 different page directories. You can see that on the slide there, the PDP, and then each of the page tables then go out. So it enables you to have basically the same virtual addressing system, but up to 64 gigs of physical memory now as opposed to 32. And so to look up, you don't actually have to go to that separate table again. It's just based in memory. You multiply by 8 because there are 64-bit entries in this case, and it's an 11-bit address. And the same deal with the C0000 page tables. Take the entire top 20 bits, multiply by 8, and go down. So this is the key right here. This code right here remaps the physical address to a new location. This is the code that actually does the memory cloak. Now, the problem with memory cloaking in this manner is that Windows maintains and performs an integrity check on the page tables when a process is shut down. So if I remap the page tables and the process dies, so what are we going to do about that? It's really lame, in fact. I thought page tables were really cool, and then when I thought of this, I was like, why did I go to all that work? This system, this new idea I had, was to simply make a 4K memory in non-page pool as called a holding pen, and when we need to cloak, we overwrite A's all over the memory in user mode, and then when we uncloak, we copy the holding pen over the memory. When we recloak, we copy it back and write the A's back again, so we just move it. And this is very dependable because it doesn't require any changes to the page tables at all. Here's a small sequence chart showing how it works. We allocate the memory, supervisor allocates the memory, puts it into user mode. When there's a cloak, we move it to the holding pen and then fill the user mode memory with A's. And then if there's an uncloak, we move it back again. Simple. Here's an example of it. I have my serial port console to my rootkit running in the screen on the side. First, the test program prints actual memory. Then the next, I cloak that memory address. You can see down there on the prompt, I type cloak in the actual address. You can see now they're all A's, and then I uncloaked it. All right, so that's the memory cloaking. Now the implant. This is the thing that goes into the World of Warcraft client. This is the code that's actually injected. How does it work? Well, first of all, it's position-independent code, similar to shellcode. When it loads, it'll parse the PE headers of all the loaded modules, and it will load up all the function pointers for a set of functions that you need to use. It subsequently loads this table of function pointers up and puts it into its own memory space. It then sets up its own memory page to be cloaked using one of our quote-unquote secret messages. And then it sets up the function, the detour hook on the render world call. And then finally, it's the code that actually executes the little microkernel for the messages. It's written entirely in C, so I have a weird little fusion system I came up with for writing so I don't have to hand code the assembly. There's a format for this. There's a header and a loader portion, and then there's the hooking code, and then at the bottom is all the data. So those are all my function pointers and strings and things that I need. It's very precise and parsable. And I actually have an example of it. The data has, for example, for functions, it has a DLL name followed by a special character and a null, then a series of function names that you want to load, followed by a null, next DLL, etc., up until the point you don't need any more of those, double null, now all your data strings, and then double null. Here's an example of that. That's the actual source code. Here I'm loading up output debug string, sleep, strlen,